Thank you so much, Professor Galoppini, for that exciting talk. And thank you for explaining the fundamentals and also sharing how this field has developed. So we have a few questions that have come in. So thank you so much, audience members, for these wonderful questions. We'll try to take as many as possible. Let's get started with a couple of questions that came in about the molecular design of the linkers in terms of how does changing the orientation of the linker modulate the behavior from p-type to n-type. A second part of that question is, how does the molecular structure of the linker affect the electron transfer rate?
Okay, so these are two different questions. So for instance, the first question is referring one of these introductory slides where this is not a work from my group. This is work from a different group and different groups. And they involve actually a different kind of semiconductor. So if one works with titanium dioxide or zinc oxide, and then you have a chromophore with an energy level higher than the conduction band, when you photoexcite the chromophore, this injects an electron in the semiconductor, so they are electron acceptor. But actually one can reverse this with the nickel oxide. So if you change to nickel oxide, you have an electron donor, so you can donate an electron to the chromophore and leave behind a hole. And in that case, you have to reverse the position of the chromophoric unit. So these are two different types of linkers have been designed for different types of semiconductors and different types of solar cells. Regarding the other question about the length, if I'm correct, right, of the linker or the structure for the electron transfer.
Yeah, how does the structure of the linker in general affect the electron transfer rate?
So, for instance, one can increase the length of the linker or introduce a saturating unit, can inhibit the injection and the recombination, if you will. The injection is always very fast, and it's in the order of really femtoseconds, tens of femtoseconds. And it's usually a very efficient process, but also the recombination can be fast in some cases. So one of the goals is to obtain a long-lived charge-separated state. And that's where the linker can play a role. For instance, there have been situations where you have you move the charge further away with an auxiliary ligand, and then with another group attached, and that can inhibit the recombination. Another aspect that can play to inhibit the recombination of the charge is to use a conformational effect. So you have a linker with a certain that undergoes a conformational change, so that after has injected, there is a conformational change, and recombination is inhibited. This is work, for instance, by Niels Damrauer has demonstrated that in a paper in 2016 with a very simple system, if you will, very simple from the design, but very, very clever. Just by introducing, for instance, insulating units, you can inhibit recombination, but you also can inhibit injection or lower the quantum yield of electron injection. So it's I make it sound as if it was easy to control this phenomena, but actually it is not. So you have to look at the molecule individually. It may be very well designed. Once you bind them, there is a high level of heterogeneity. When you study these interfaces, unless they're monolayers, they are mesoporous films. So you have a population of molecules that binds with like these cartoons, but you have also a population which they are laying down and they do not do what they're supposed to do. And so it sounds that you can do anything you want. And then in practice, it's a little bit different.
Yeah, very true, very true. So Professor Galoppini, another question that came in was about the state of the art in this field. So the question is, if you could give the audience an idea of the structure-performance relationships, meaning what kind of molecules would exhibit very high performance as per the current state of the art in the field?
I think it depends on what application you're looking at. As an example, if one looks at these still at the dye-sensitized solar cells that are now really more of a niche, as I said, they're not, they never reached the efficiency that one was hoping for. The state of the art are these non-metallic dyes, these push-pull dyes. The one that I've shown in the slide is one of the first, but now they're very sophisticated. So really the state of the art are these push-pull dyes that can actually be mixed to obtain absorption that almost in the near IR, and that can be designed to inhibit recombination or aggregation phenomena. So I would say from non-metal, purely organic systems, these are the most, the ones that I believe that are more efficient.
Okay.
And that's one example of this area. But I think obviously I'm not familiar with the area of perovskites, but I think there is a lot now going on with these interfaces for perovskites materials.
Professor Galoppini, we understand we are close to the end of the hour, but if we could request a few more minutes of your time, because we are having a lot of questions, would that be okay?
Of course.
Okay, thank you so much. And the question that has come in is, what approaches are to be kept in mind to reduce recombination rate to design organic small molecules for photovoltaic applications?
That is always a bit the problem, the recombination. So in some inorganic complexes, the recombination is fairly slow, but in organic molecules, it is. Interestingly enough, that host-guest approach that I've shown exhibited very slow recombination rates, but it's not practical. It's more of a academic exercise and a beautiful supramolecular exercise, but it's not very practical. I think conformational effects are very promising, where the linker can undergo a conformational change or another change following injection that prevents recombination. So this is an area we are working on, and I think that that's a promising approach.
Thank you, Professor Galoppini. Because we talked about the interface quite a bit, and of course the interface rules in these kind of systems, there is a general question, in summary, what do we actually want from the formed interface? Is it a great charge transfer always favorable, or should it be tailored to each specific application we have at hand?
Great charge transfer.
Do we want a good charge transfer always? Is that the favorable state we are looking for, or it depends on the application we have in mind?
It depends, I would say, on the application. So I'll give an example. I'm not working in the area of solar fuel or photocatalytic systems for CO2 reduction or water splitting. But these are, for instance, many of these photocatalysts involve an aqueous environment. In that case, one of the key issues is the stability of the interface, is really how strongly they attach and whether they desorb during this process. So the design of a strong anchor group is still of interest. I would say long-lived charges separate state, it's always of interest, especially for photocatalytic systems, because you have time to do chemistry. It's one of the big objectives in, for instance, in systems that want to mimic photosynthesis, obtain long-lived and at a long distance charge separate state. So in general, the injection is always fast. It's really to obtain a long-lived charge separate state and an interface that is stable chemically, that doesn't degrade. So there, I would say there are many parts that one has to control.
Thank you for those insights, Professor Galoppini. And the question is, how does the chromophore metal oxide interface help in improving the photo conversion efficiency? Can you use chromophores with a relatively large band gap in a device?
Yes, so it's one of the aspects. You can harvest a larger portion of the solar spectrum, but then it's one of the advantage. One of the things that are of interest. In this case, we are talking about, obviously, I'm focusing probably a little bit too much onto the dye-sensitized solar cell, which is a bit the older chemistry in this area. Yeah.
So Professor Galoppini, just moving slightly away from the organic molecules, a question of the TiO2 or the nano oxide surfaces. So the question is about, what if we have polycrystalline TiO2, which consists of more than one crystal plane direction? Will it be possible to direct the linker on it?
You're talking about the dipole effect on titanium dioxide?
Yes, TiO2. If the TiO2 is polycrystalline, do we face any challenges in directing the linker molecule onto it?
If the question is about the dipole, yes, there are challenges. So the experiments that were done, it doesn't mean that cannot be done, but the experiments that were done were so far in my group were proof of concept on a monolayer. So that's the easy, right? Easy not to make, but easy to measure and to observe a significant shift in this case, because they are all aligned and so on. When we're talking about the polycrystalline nanostructure, there is not only orientation effect, but also they become very, unless you have a very large dipole moment, they become quite, you have a lot of physisorbed molecules that are not perfectly oriented. So I would say that this approach would work better on a planar surface rather than on these nano crystalline devices. That's obviously a limitation, a disadvantage, but there could be approaches possibly to limit that. The molecules that we have been studying are very big, so that never works very well for these porous systems. If they were small molecules with a large dipole, then I think it could work also on these nanocrystalline. And it has been demonstrated actually on nanocrystalline compounds. So it's not that it doesn't work.
Professor Galoppini, some more interest on the TiO2 system. Some of our audience members are asking if there are other metal oxides that can be used, for example, tin oxide or molybdenum oxide, and if layer double hydroxides can be used in such systems.
So it depends on the wide band gap. So titanium dioxide is the most used for these photocatalysts and for these earlier work on solar cells, just because the band gap and so basically it's an inexpensive material. There are many aspects in favor of titanium dioxide. So the band gap of titanium dioxide and zinc oxide is 3.2 electron volts. It's very similar, and energetically they behave in the same way. When you cast these films, they are optically transparent, so that's why you need a chromophore to absorb visible light. Sunlight, you need something that actually absorbs in the visible. The tin oxide also can be has been used. There are tables of oxide with different band gaps, and that determines the application. I would mention that there are other aspects. For instance, zinc oxide, it's actually excellent. From many point of view, has a very attractive morphologies, it looks like a carpet, like a needle. It's vertically aligned with a fast electron transfer, but they etch easily. So that's why many of these fundamental experiments are done on titanium dioxide. It's a kind of the system that works well, but definitely there are other metal oxides. When we want to study the excited state, meaning you excite the molecule and the fluorescence is quenched onto titanium dioxide. But if you want to study the fluorescence on a similar metal oxide interface to understand better this behavior, we use, for instance, zirconium oxide, which has a wide band gap, about 5 electron volt, and that leads to, it's almost like an insulator, or aluminum oxide. So I just picked, 2 examples, 1 or 2 examples, yeah.
Thank you, Professor Galoppini. We also received a couple of questions about the journal, Applied Optical Materials, so I'll combine both of them together. One of our audience members is asking if Applied Optical Materials will be interested in studies on designing interfaces with potential applications where extensive applications may not be demonstrated. And another question came up on a similar line, studies on spectroscopy and photophysical properties and applications of nanomaterials. For example, papers that are typically published in Journal of Physical Chemistry or the sister journal ACS Applied Nanomaterials. If you can give some insights on nanomaterial systems and their photophysically active systems, which might be suitable for applied optical materials.
So first, regarding the application, so the title of this entire portfolio of journals is Applied Materials, right? And then interfaces, applied biomaterials, and so on. The application doesn't have to be demonstrated. You don't have to show a functioning device. You can show an interface that is carefully characterized and has optical properties and application, and put it in a context with a nice introduction, how this is relevant to a certain type of device or a certain type of application. Second, we have a lot of our manuscripts that we are receiving and accepting or considering for publication involve nanomaterials. Obviously, there is a big overlap. A lot of optical devices involved are on the material on the nanoscale. So where does overlap with the nanomaterials with our journal? Actually, there can be sometimes overlap. Sometimes we, between editors, for instance, from one journal to the other one, we receive a manuscript and for instance, if I receive something on dye-sensitized solar cells, even though it's an optical application, I think this is actually which audience would enjoy this manuscript better, our journal or applied energy material. Probably applied energy material would be a better venue because would be read by the community and would receive more reading, more citations. So we refer that to the journal. So if we have a nanomaterial and the focus is not on the nanoscale, but on optical properties, we get the manuscript because it would be read and enjoyed by a community that would appreciate it better. So the ultimate goal is, I think every manuscript of good quality has a place where to be published, but it has to be selected so that it fits the scope of the journal. And it's for the author interest, because then people will read it.
Thank you so much, Professor Galoppini. We still have so many questions flooding in, but in the interest of time, we'll have to close the session. So I'll request if you may have any final comments or thoughts for our audience members or the potential readers and authors for ACS Applied Optical Materials.
I would say that start reading the manuscripts. It's a young journal, and it doesn't have impact factor yet, right? It's not even 1 year old, but still consider it, because and see it grow. It's something that probably the best thing is to start reading it and see whether your work fits the scope of the journal. We will be updating with editorials, how the journal is growing, and follow us, because we are having some forum issues, spotlights on applications. So not just research articles, but reviews and issues, even with other journals of MI family in the future, that are aimed to bridge different type of authors. And follow us, I would say, on by reading. And if you have questions, you can contact me directly. I'll be very happy to answer.
Thank you so much, Professor Galoppini. With that, we are coming to the close of the session, and I'll hand over to my colleague, Dr. Kunal. Over to you, Kunal.
So thank you, Asha. Thank you so much, Professor, kind of sticking around for another 15 minutes. We're really thankful to that. As you can see, a lot of reactions coming in from our audience members with a lot of thumbs up and claps. So thank you so much. This brings us to the end of today's session. We hope that you have enjoyed this broadcast. We invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of the session, you will receive a brief survey. Kindly share your feedback with us so that we can continue to improve and serve you better. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS events. Until then, stay safe and healthy. Bye, everyone.